Hello, everyone. I'm Wei Zhong, and today I'm going to give you a talk about the history of astronomy. So, welcome. I'm happy you can join us. And today, let's take a dive back in time and find out all the people, events, and ideas that brought us the astronomy as a discipline of science that we all know and love today. So now before I begin, let me just make a quick, let me just be clear about today's talk, right? We're going to be focusing more on astronomy in a Western civilization since the scientific revolution. Now that's not to say that other civilizations like the Chinese or the Muslims have not made significant contributions. It's just that the system of scientific astronomy that we pursue today is a direct succession from that of the Western civilization's astronomy in history. And so with that, let us begin. So now let us turn the clocks of time all the way back and we go to the beginnings of astronomy. Now that brings us to the idea of geocentrism. Now, honestly, right, in the history of astronomy, one of the most important chapters is the rise and fall of geocentrism and its eventual replacement by heliocentrism. And that was a very, very important part of the development of astronomy in history. So what is geocentrism exactly? Now, geocentrism is the idea that the Earth is at the center of the universe. It is static and unmoving, and everything else is moving around us. Everything revolves around us. The stars, the planets, the sun, and the moon. Everything revolves around Earth. So that was the idea. Now, to modern civilization, it might seem a little strange. This idea might seem a little against logic, but back then it made perfect sense. Why? I mean, okay, the simple idea is this. Now look at you, look around you right now. Are you aware? Do you feel like you are actually zipping around the sun at 31 kilometers per second? Or are you whizzing around the equator at 1,600 kilometers per hour? You probably don't, right? So to them, it felt like the Earth was unmoving. We are at the center of the universe. We are not moving. Everything else is revolving around us. So that was the rise of geocentrism. And that was how the idea came about. So there the idea went. But the thing is, in this model, there was something that couldn't be answered. And that was the phenomenon of retrogression. Now, what is retrogression, actually? Now, retrogression is the phenomenon that we can observe, right? When planets are drifting across the sky, sometime at some part of their orbit, they will appear to us, okay, from our line of sight. They will appear to suddenly move backwards a bit, and before long, then loop and hit in the same direction again. So why was that? Why did that happen? They couldn't explain it using the geocentric model. So eventually, Greek astronomer Ptolemy in 150, approximately circa 150, the year 150, he came up with the Ptolemaic system of geocentrism. Now you can take a quick look at the diagram on the right, which is an exemplification of how the geocentric model then looked like, the Ptolemaic system of geocentrism. Essentially, you had an epicycle right there. Okay, so that epicycle was essentially like a halo orbit that the planets orbited around as they moved around the deferent, which was the big orbit. So there, at some points of the orbit, when the planets were closer to Earth, they appeared to move in the opposite direction of their orbit, and that was how they explained retrogression. And to them, that made sense. Okay, so for the next 1,400 years, that was the idea that caught up, and that became the default of the model of the universe. But during that period, during that period when geocentrism was supremely dominant, there were a few individuals who actually tried to contest it and came up with other theories of their own. And one of them that we will talk about today is Aristarchus. Now, Aristarchus was an ancient Greek philosopher who actually came even before Ptolemy, okay, about 200-300 years before. And so he maintained that the Earth, everything didn't go around the Earth, rather everything went around the sun, okay? And he suspected strongly that the sun acted as sort of a central fire to the planets. And he even went on to hypothesize correctly that the stars we see in the sky were also other suns. He probably drew an inspiration from campfire when you see a lot of people would surround a campfire and the campfire would be radiating heat and light out to everyone. And then as you moved away from the campfire, it went from a whole burning fire to eventually a spot of light in the distance as you moved away. But unfortunately, while in retrospect, his theories were correct, back then it attracted very little attention because it seemed to rebel logic then. And as the Ptolemic model came to mainstream a few centuries later, heliocentrism would then be sealed away for over a millennium. And now we move on. We fast forward to the dawn of astronomy as a discipline of science, at the beginning of the scientific revolution, and we talk about some very, very important people who revolutionized astronomy as a domain and brought us what we have today. Who are these people? Here, these four. Now, who recognizes them? Is there anyone who recognizes any of them? Maybe the first and the fourth might seem a little more familiar. Maybe the second one is a bit more obscure, but don't worry, we'll cover all of them because they are all extremely instrumental to the development of astronomy. So let's begin with the first one, okay? The first one he's called Copernicus, okay? Many of you might have heard of him before. The Copernican revolution is named after him. The second one, maybe not so many of you might have known, but he was just as important. His name was Tycho Brahe. For those of you who are familiar with the moon, the most prominent crater on the moon is actually named Tycho crater after him, okay? And then we have Johannes Kepler and Galileo Galilei. So now let's dive into them, their stories. Nicholas Copernicus, he was the man who first put the sun in the right place. Not exactly the right place, but in the universe, but relative to the solar system. He was a Polish astronomer and was the first in history to provide the familiar model of the solar system as we know it today, and actually provide coherent and logical explanations that are backed up by mathematics and sound logic. Now, the namesake Copernican revolution opened the doors to modern astronomy, and for the first time over 1,000 years, Earth was not at the center of the universe. Let's find out a little more about him. Now, in the time before Copernicus, when the Ptolemaic model reigned supreme, no one really dared or even needed to challenge the Ptolemaic system. It was unnecessary, it made perfect sense, and more importantly, it was endorsed by the church. And no one dared to go against the church because that would be heresy. But Copernicus was slightly different. Well, he wasn't exactly very high profile with his theories, but he still had immense creativity and mathematical inclination to put forward the first ever coherent and comprehensive model of heliocentrism. Now, if you see on the right, that was his model of heliocentrism as he sketched it himself. The sun was in the middle and the Earth would be the third object from the sun. Okay, he wasn't exactly right in the fact that he put the sun at the center of the universe, which now we know it's not at the center of the universe. There might not even be a center of the universe. But and he also assumed that the orbits were perfect circles. But at least he was able to provide a model which we are all more familiar with today. And using this model, he actually realized that a number of problems, such as retrogression that we talked earlier, will be solved very elegantly. How would retrogression be solved? Essentially, when an inner planet moves faster than outer planet, the outer planet will appear to move backwards. Okay, imagine yourself on an expressway, okay, and you're driving faster than the car next to you. So that car will actually appear to move backwards and backwards relative to you, right? That was the same idea. And he also realized that the strangeness and movements of inferior planets, especially Mercury and Venus, would be solved just as easily. How? Well, essentially they are orbiting closer to the sun than the Earth, so therefore they will always appear close to the sun and will only appear in the evening after the sunset or in the morning before the sunrise. So that was a simple model of heliocentrism that he put across, and he provided the geometrical explanations and basis to explain the behavior of planets in the night sky. But the thing is, his theories were so groundbreaking at that time that a lot of people just didn't buy it. He didn't publish his theories, but he told his close friends about it, and everyone was shocked. When they first heard of heliocentrism, they challenged Copernicus that if heliocentrism was to be true, okay, then we should be observing the stars in the sky moving and shifting to different positions. Now, that idea that they're referring to is called parallax. Okay, the idea of parallax is actually very, very simple. Now, reach out your thumb, okay, and then you close your left eye and look through your right eye, and you close your right eye and look through your left eye. So essentially, you will realize that the background relative to your thumb your thumb relative to the background actually shifted a little bit. So that was the idea behind parallax altogether. And they thought if the Earth was moving around the sun, that at different points of the orbit of Earth, we should be seeing the stars moving as well. But why isn't that happening? So Copernicus rebutted that incorrectly that while those movements existed, they were simply too small to be observed. And no one bought that. The simple reason is that, well, back then the universe wasn't thought to be that big. It was pretty finite and pretty small. So people thought that if Earth was truly moving, we should have been already observing the movements of the stars. And unlike what Copernicus claimed, that it will be too small to observe, it should be observable. Well, time would prove that Copernicus was right. And 200 years after Copernicus's death, the humans had the first ever confirmed measurements of parallax. And despite the groundbreaking theories that Copernicus put across, he never quite found the motivation or courage to publish his work until the year of his death. And even then, his theories, while groundbreaking in retrospect, they weren't well received simply because they were too technical and rebelled logic and rebelled religion at that point in time. So it took a next generation genius to carry on and refine his legacy. Now, who was that next generation genius? Before we get to him, let's talk about another person. His name was Tycho Brahe. Okay, and he was one of the greatest astronomical observers in the era predating telescopes. Okay, he didn't come up with any groundbreaking advancement to heliocentric theories. In fact, he was a staunch opponent to it, as we will soon see. But yet, his impressive observations and records of the night sky were pivotal to the emergence of modern astronomy. And without him, little that succeeded him would be possible. How was that? Well, Tycho Brahe was himself a very wealthy Danish nobleman. He had a knack for crafting things, for craft work. If he was today, he would probably be a very outstanding mechanical engineer. So at the same time, he also found a lifelong passion for stellar observations and stargazing. So he used his craftsmanship to feed into his love for stargazing, and he crafted ever larger and more sophisticated tools, bigger and better than the world had ever seen. And with those, he observed the stars night after night and created the most robust record of planetary positions in the pre-telescopic era. But as we mentioned, well, the heliocentric theories. Why? Because he thought, you know, my instruments are so big and so good, okay? If the Earth was moving, well, I should have been able to observe parallax, but I didn't. Therefore, well, heliocentrism cannot be right. That was his line of thought. So he formulated an alternative called the Tychonic system, which we now know it as, and you can see a model of it on the right. Okay, it's actually kind of a hybrid between Ptolemaic and Copernican models. And while it was not entirely right, it was not right. Well, it was actually kind of brilliant if you see it. The Earth was still at the center of the universe. Okay, the Earth was still unmoving and static. At the same time, the sun and the moon revolved around the Earth, and the planets revolved around the sun. Okay, he created this because he couldn't accept the fact that heliocentrism was right because parallax was not observed. But at the same time, he couldn't fight the appeal of the heliocentric model in explaining retrogression as well as the behavior of the inner planets. So there, that was. And let's take a look at the kind of instruments he had in observing the sky, right? Here you have a Tycho sextant as well as his armillary. Now, sextant is the equipment that he used in order to measure angles and positions of objects in the night sky in order to determine their positions and track them over time. Whereas on the right, you see an armillary. It's actually kind of a simulation of the night sky where you can actually freely move these chips inside and simulate the movement of objects across the sky. And so these were some of his equipment, and those were the largest and most sophisticated in his time, and gave him the most accurate observations ever. And with these astonishingly accurate observations, he was capable of predicting celestial events to a great degree of precision. So Tycho is undoubtedly the greatest observational astronomer in the pre-telescopic era. Now, till this day, the most prominent crater on the moon is still bearing his name in remembrance of his contributions. Unfortunately, he died in 1601, allegedly of a burst bladder, and his work eventually fell to that next generation genius to continue. And fortunately, they managed to build a connection and allowed Tycho to hand that genius his work. Who was that genius? Johannes Kepler. So the works of Copernicus and Brahe eventually came to Kepler. With his sheer brilliance, he generated the most rigorous proofs of heliocentrism and provided the first models of planetary motions, which were sufficiently accurate to provide an inkling of an attractive force that would be known as gravitation decades before Newton came along. Let's find out a little more about him. Okay, so Kepler was ever since young, he was a prodigy in geometry and mathematics in general. And when he was exposed to the Copernican system, he was obsessed with attempting to refine it. And he was so obsessed that he eventually came to calculate and memorize the ratio of the distances between planets by heart. Okay, not the distances between the planets, it was still unknown then, but the ratio of the distances between the planets. So one day when he was teaching, he eventually grew up to be a teacher in this place called Graz in Germany. So one day when he was teaching in the school in Graz, he suddenly thought, hey, I think I'm going to figure out what the ratio is about. He suddenly realized, hey, what if I inscribed a polygon in a sphere, and that sphere in a polygon, and another polygon in a sphere, and a sphere in a polygon, and so on? I would eventually come up with a ratio between the planets. So his idea, he was so excited that he thought he had unveiled the grand plan that God gave the universe. And he went home, immediately noted it down, and started to work on his first publication, now known as the Mysterium Cosmographicum. So on the right, you can see the diagram, the visualization of what his idea was. And little did he know that eventually he will come to actually overthrow this theory. But nevertheless, during that time, this theory made its way to Tycho Brahe, who was impressed enough to eventually offer Kepler an informal job. Not without a bit of unpleasant negotiations, but eventually they collaborated. And Tycho agreed to give a portion of his observations to Kepler's for him to work on. And the part of the data he provided was the positions of Mars. And that turned out to be crucial. Why? Because it comes down to the idea of eccentricity. Okay, eccentricity is the idea of orbits being ovalish. Now, planets in the solar system or anywhere else actually, they don't really orbit their main parent body in perfect circles. Okay, they tend to be slightly ovalish in shape, and that in ovalish in astronomical terms we call it as eccentricity. And the most ovalish orbits in the solar system, number 1 belongs to Mercury, number 2 belongs to Mars. Okay, all of the other planets are mostly fairly circular, okay? And that was the point that led Kepler to begin overturning his theory and come up with even more accurate ones. So while working on the data provided by Tycho, he found that Mars positions weren't exactly as predicted. They were not perfect circles. So most other astronomers could have probably just dismissed it. It's just a mistake in observations or something. But Kepler believed that he was working with one of the most competent observational astronomers of that time. So he believed that there was something else going on. Digging further, and he eventually discovered the fact that planets' orbits were not circular and that their orbital velocities varied with their distance from the sun. And eventually, this developed into Kepler's laws of planetary motions, and which he published in Astronomia Nova in 1609. A few years after Tycho died, the emperor of the Holy Roman Empire, Rudolf II, eventually allowed Kepler to access the rest of Tycho's data. And with them, Kepler compiled the Rudolphine tables based on those laws as well as Tycho's data, which offered precise computations and predictions of planetary positions. So here on the right, you can actually see the cover page of the Rudolphine tables. Okay, if you look closely, he actually paid tribute by writing down the names of a few people who he thought contributed to his success. You can see Copernicus, Tycho, Hipparchus, and Aristotle, and apparently there are a few more up there. Yeah, so that was Kepler's contributions, and he would be known as one of the most pivotal figures in the beginning of the scientific revolution. And in his later years, with the invention of the telescope and the correspondence with Galileo, who we will talk about in a bit, further cemented his theories and belief that heliocentrism must be right. And today he is remembered as one of the most pivotal figures in the emergence of scientific astronomy. Now moving on, we have Galileo. I'm sure many of you have heard of Galileo before. He is known as the father of modern science, and he absolutely deserves it. He developed the basic concepts of physics and paved the way for modern science, and most importantly to astronomy. He was the pioneer in turning the newly invented telescope to the night sky, and that forever changed the way humanity viewed the universe. Let's find out a little more. So he had a lot of different notable achievements in the realms of physics, but today we're going to be focusing exclusively on what he did in astronomy. So when he learned of the newly invented telescope, he crafted one and designed one himself, which would now be known as the Galileo scope. Okay, and he was the first one ever to use the scope to make observations of the moons in 1609. He also made the first ever observations of Jupiter's moons in 1610. So the first time when he was looking, when he was looking at Jupiter, he decided to take a closer look, and he realized it's a strange thing that, you know, for those of you who have seen Jupiter through a telescope, right, it's one big center block, which would be Jupiter, followed by a few smaller stars in line around it. So those were actually Jupiter's moons. Back then, Galileo didn't know that. He thought, what are those little stars up there that somehow coincidentally are in line with Jupiter? Strange. So he came back the next day and he found that the stars are still there. What's that? Well, he couldn't explain it. So night after night, he came and observed again and again and again. And he found that those stars are actually moving and they are still in line with Jupiter all the time. And what's more, sometimes there were 4, sometimes there were 3, sometimes there were even 2. And he couldn't explain it. So eventually he found out that these moons were actually following a circular motion around Jupiter, which meant that they were actually orbiting Jupiter. They were going around Jupiter in regular circular motions. So using this discovery, he extrapolated his findings, and he thought, if these moons can be orbiting Jupiter, we can too be orbiting something else, like the sun. Suddenly, heliocentrism had another logical backing to it. And in addition, with his Galileo scope, not only did he observe the moons of Jupiter, he also made the first ever close-up observations of the moon's surface, the phases of Venus, the sun and the sunspots, as well as the rings of Saturn, even though he didn't realize that they were actually rings. He thought they were ears or moons going around Saturn. And he also witnessed countless of stars making up the Milky Way that lay way beyond naked eye. So unfortunately for Galileo, well, he was in Italy and he was born into a period when the Catholic Church's authority was indisputable and overbearing. And in Italy, their authority was omnipresent. So the geocentric view that the church espoused was had to be correct, and Galileo's view of heliocentrism must have been wrong. And despite the courageous attempts of Galileo to defend the heliocentric model, he was faced with inquisition and prosecution by the church and was put on house arrest until the day of his death. But no matter what, his contributions to astronomy meant that geocentrism had actually met its inexorable decline, and he remains one of the most influential scientists till this day. Now we see that heliocentrism and the universe as we know it is starting to take the shape that we are realizing and that we know today, and also that the discipline of astronomy is quickly becoming an independent domain of science. And time for things to pick up a little more and for us to make sense of the universe. Which brings us to Isaac Newton. I believe I don't need to say too much about Isaac Newton. He was an amazing scientist who had fundamentally transforming effects on mathematics, physics, and astronomy. And he introduced a whole new era to science, reigned on the classical system of Newtonian mechanics, which he founded and is named after him. For those of you who hate calculus and calculus class, well, here is one of your masterminds, okay? Yep, you have him to thank. So he was born on Christmas Day of 1642, which happened to be the year that Galileo died. So in a classic 16th or 17th century style conspiracy, people actually thought, hey, what if Isaac Newton was actually a reincarnation of Galileo and who was back with a vengeance to make even more science? Well, there was a conspiracy, okay? So ever since young, he was a queer prodigy. Even after growing up, he was kind of a strange person as well. He ever experimented by looking at the sun for several minutes and almost went blind. And in another event, well, he stuck a needle into his eye to check out what was in the eye socket. Well, his poor eyes, but fortunately, well, they accompanied him to the day he died and allowed him to make discoveries about light. So key to his accomplishments were the development of calculus. He explained the continuous spectrum of light, and in astronomy, he was the first one to model gravitation and celestial mechanics. Now, nowadays, I'm sure you have heard the story of the apple falling on his head. Unfortunately, well, historians are starting to dispute, and that might never have happened. Okay, so yep. his theories of gravity, he did still come up with very coherent theories of gravitation, and which is published in his work Principia in 1687. And that gave rigorous interpretations to Kepler's laws of planetary motion. He also invented the Newtonian Telescope, which is a reflector telescope that uses mirrors to reflect light. So Galileo's telescope was a refractor, which used lenses to refract light to a single focus point, and you will observe from there. While Newton's telescope used mirrors to reflect and focus the light to a point, and this will be the point of observation. So that solved the issue of chromatic aberration, and also allowed future telescopes to be built ever better and bigger. So, well, Newton's impact on science, as you see here, cannot be overstated. His theories were the nail in the coffin for geocentrism, and he ushered in the apogee of the scientific revolution. And from then on, science, and including astronomy, would never be the same again. So with that, we can see that astronomy has become a very consistent and independent domain of science already. And now let's talk about another few people. Oh, okay. If I've seen further than the others, it is by standing on the shoulders of giants. That was what Newton said. And the giants were the people who came before him and paved the way for him to make his discoveries about nature. Now we talk about a few impressive family, in fact. These three that you see here, we have William Herschel, Caroline Herschel, and John Herschel. So Caroline was William's younger sister, and John was William's son. So three of them were very, very important to astronomy in the modern day. So William Herschel and the Herschel family was initially from Germany. Then they moved to England, and William Herschel turned from a musician to a self-taught astronomer. Now he began his astronomical journey by learning how to craft his own mirrors, polish his own mirrors, and craft his own Newtonian telescopes. Okay, and in the process, he managed to interest his younger sister, Caroline Herschel, who would go on to accompany his astronomical endeavors for the rest of his life. Now, for those of you who might be in contact with the amateur astronomy circle in Singapore, you might know this in our weird lingo known as the fact that Caroline was figuratively poisoned by William. Okay, figuratively. Okay, now William began his observations in 1773 with early interest in searching for double stars. Now, double stars are stars that look very, very close together. Okay, they may be physically bound to each other through gravitation, or they might simply be stars that are from our line of sight, appear to be very close together, but are actually not associated with each other at all. So day after day, he would look at the skies through his telescope, and his first breakthrough came in 1781. One night when he was observing, he suddenly saw a blue blob. Like, what was that? It didn't look like a star. What could that be? Maybe a deep sky object or something like that? He wasn't sure. So for the next few days, he came back again and again to observe that object, and to his surprise, that object was moving. So he thought, maybe that's a comet. You know, comets are a part of our solar system, and they move too, so that might be a comet. So he told a few of his fellow astronomers about it, and these fellow astronomers went to help him to compute the orbit of this new object. And they realized this object is too far out, and its orbit was too circular to be a comet, because a comet tended to follow a very ovalish and thin orbit, coming into the inner solar system, then swinging out again. But this object wasn't like this. And that was when they realized that might be a new planet. So, and that was absolutely groundbreaking and shook the world at that time, because that was the first time in history that the boundary of the solar system extended beyond Saturn, and that was the first time that the solar system suddenly doubled in size. So eventually they came to call that planet Uranus. Unbeknownst to them, this would eventually become the butt of many jokes in a few centuries later. So with their telescope making skills, William and Caroline constructed ever larger and better telescopes, and eventually they built Herschel's very renowned 40-foot telescope. So that telescope had 120 cm in aperture and objective size, and had a 12-meter focal length, and its entire length of the tube itself was 40 feet across. That's why it's known as the 40-foot telescope, and that would be the largest telescope in the world for the next 50 years. And so with their telescopes, they scanned the skies night after night and discovered scores of new objects. And they surveyed, and while surveying the skies, they realized that there was a solid evidence that we actually lived in a disc-shaped galaxy of stars and not within a physical, evenly distributed celestial sphere. Okay, in the past, people didn't know that the Milky Way was made of stars. So they looked at the sky and they thought, you know, these stars that are visible to us, they seem to be evenly distributed across the sky. So the celestial sphere must have been evenly distributed, and that matched the view of that God had created a perfect world for them. So that was a theory then, but Herschel, through his repeated observations, he found that there were actually way more stars in the plane of the Milky Way. And he set out to survey the distribution of the stars, and eventually he came up with a model of the Milky Way. And here you can actually see his model of the Milky Way. Unfortunately, it's nothing like we know today. And he put the Earth here in the middle, in the black spot in the middle of the galaxy. While nowadays we know that the solar system is actually about 2/3 of the way from the center of the Milky Way. But still, good attempt. And they still managed to discover the disc-shaped property of the Milky Way. And after both William and Caroline's deaths, William's son, John Herschel, he continued their legacy and added on several new discoveries to the record. Unfortunately, he didn't make as many contributions as his father because he also had another interest in botany, but still they were remarkable. And eventually this massive set of records would be later published as the New General Catalogue, known as NGC. And that remains one of the most referred to catalogs of deep sky objects till this day. So some of you, when you are stargazing, looking at a star atlas, you might see some objects labeled as NGC blah, 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 blah. Okay, so that is where the NGC prefix came from. Now, you know, it was discovered by Herschel and compiled and published. So I would like to make a side note to Caroline Herschel. She was perhaps one of the most impressive women of her time. Not only was she an indispensable aid to William in their early days of observations, she eventually went on to make many, many discoveries of her own. And she was also the first woman in England to hold a governmental position and to receive receive her own wage from the government as a scientist. And in an age where society and politics was prejudiced against women in general, I think that her accomplishments were extraordinary. So yeah, and let's move on. Here are some more notable people, events, and ideas. Let's say in 1655, Christian Huygens recognizes the ring form of Saturn's rings. Remember just now we said that Galileo actually thought they were ears or moons orbiting around Saturn, while Christian Huygens discovered that they weren't, they were actually rings. In 1761 and 1769, Venus transits allowed the determination of the distance from the sun to the Earth by trigonometry, and that distance would become known as the astronomical units, AU. Okay, and that was based on the predictions and methodologies suggested by Edmund Halley. In 1838, Copernicus was finally vindicated when the first confirmed measurements of parallax was published. In 1846, Neptune was discovered, and this was the first time ever that the planet was discovered by mathematical modeling. And throughout the 19th century, spectroscopy was developed, and that allowed spectroscopy is essentially the science when scientists would look at the color of the stars, and they would see within the spectrum of the stars what colors were emitted or missing, and therefore they can tell what elements are there in the star. So that was the birth of astrophysics. And with spectroscopy, in 1868, helium was discovered by observing the sun by the scientists Jules Janssen and Norman Lockyer. And now we begin to step into modernity, what we are familiar with today. So let's talk about the Great Debate. Now, during the late 19th century to the earlier 20th century, scientists were mostly believing that the universe wasn't that big. So the Milky Way essentially filled the entire universe, and there was nothing else beyond that. Those nebulae, some of the nebulae we saw that follow a spiral shape, which now we know as independent galaxies, they thought they were simply nebulous gases and clouds within the Milky Way. Okay, but there was a small share of scientists, who thought that these spiral nebulae actually are not structures within our Milky Way. They are galaxies in their own right. But that would mean that the universe was in fact much larger than thought. And at that point in time, most people did not like that idea. So the Great Debate was held between the two camps of astronomers in 1920. And unfortunately, on the day of debate, there was no conclusive evidence to settle the matter. But it was until 1924 when astronomer Edwin Hubble, after whom the Hubble Space Telescope was named after, he observed the apparent magnitudes of Cepheid variable stars, which are essentially stars that that fluctuate in brightness with a fixed luminosity at some distance away. So taking a look at the luminosity and the brightness of these stars, he calculated that some of these stars are too far to be within our own galaxy, and they must have been galaxies in their own rights. Okay, one example would be the Andromeda Galaxy, okay, which he found to be 2.5 million light years away, definitely not part of the Milky Way, and the universe was definitely larger than thought. And so the size of the known universe suddenly grew tremendously. So here you can see a picture of Edwin Hubble at Paloma Observatory, as well as a picture of the Andromeda Galaxy kindly provided by my friend Honey. So they were already surprised in 1924 that the universe is so big, it's much larger than we thought. But in 1925, Hubble again observed not only was the universe bigger than we thought, it was expanding. How did they know they were expanding? He looked at the spectrum coming from the distant galaxies, and he realized that everything seemed to take off a reddish tint. So that was because of this phenomenon called redshift, indicating that these galaxies were actually moving away from us. And what's more, he found out that the further these galaxies were away from us, the redder they looked, which means the faster they were receding away from us. And which means that the expansion of the universe was actually accelerating, and that became known as inflation. So such a discovery indicated that the universe is not static, unlike previously thought before Einstein. So extrapolating this expansion, so at some point in the past, it must have been smaller, right? Now it's expanding. In the past, it must have been smaller and smaller and smaller and smaller and smaller, which eventually brought out the idea of the Big Bang. The Big Bang was an era when the universe did not exist, when space was compacted into a singularity that was extremely tiny, and bang, the universe existed. So that was the Big Bang theory. And by modeling the expansion of the universe, they eventually found out that the Big Bang occurred 13.8 billion years ago, which is now the age of the universe. So the issue of Big Bang, well, there was no evidence to support it at that point in time. So it was still a hypothesis, a guesswork. Until in 1964, two astronomers, Arnold Penzias and Robert Wilson, they were working on radio communication antenna to communicate with satellite. But they were frustrated to hear that, I'm trying to listen. Why is there a background noise that I can't get rid of? So they put shields around the antenna. The noise was still there. They went around the households in the area. Sorry, can you turn your radio down and everything for us to listen? And they listened, and it was still there. So they looked at the antenna and realized, hey, what if it's the bird poop? It's been under the sun for so long. There's a layer of bird poop on top. Maybe that's interfering with our signal. So they want to clear it up. And unfortunately, well, that still didn't solve the problem. And they were so annoyed, but they just couldn't find the cause of it. So one day they thought, hey, there was this theory about the Big Bang, and the Big Bang might have left some energy over in the form of microwave radiation. So they quickly contacted the nearby physicists Robert Dicke and James Peebles, and together they recognized that these noises were actually microwave radiation remaining from the Big Bang. Okay. In fact, in our regular households, if you turn a radio to a channel that is not receiving reception, you can actually hear like a part of the noise that you're hearing, the noisy sound that you're hearing is actually remaining signal from the Big Bang, and it's detectable. Okay, so this was at that point in time the strongest evidence that supported the theory of the Big Bang. And till this day, observations of these microwave background continues to allow us to probe deep into the universe's past. Here is the picture of the distribution of the cosmic microwave background. So essentially, people call it as one of the maps of the universe, showing us which areas are radiating the most microwave background towards us. And with that, we come to today. Thanks to all these people and events and ideas that we've had before, humanity has now looked deeper into space, reached greater heights, and mastered vastly more knowledge about our place in the universe than ever before. Now, note that all that I mentioned are not exhaustive. There are countless more people, countless more events and ideas that were instrumental to the development of astronomy that we have to thank too. And it's because of them that today we have millions of telescopes scanning the skies every night. We have tens of thousands of professional astronomers and astrophysicists globally to study the universe. And thanks to them, we have new discoveries about the night sky that are made almost every day. Maybe a new asteroid, a new supernova, black hole, a new theory has been formulated, a new picture of a phenomenon has been imaged. All these, we have the people and events and ideas that came before us to thank. So yes, thank you very much. That's the end of my talk today. Thank you for coming. I hope you enjoyed it and I hope you learned something from it. And feel free to follow NUS Astronomical Society at the accounts below or follow me at there. And with that, on this note, thank you very much and have a great weekend ahead. And I'll see you next Friday when we'll talk more about space exploration. Thank you very much.
Okay, guys. So I'm giving an offer. Okay. Yeah. I'm giving observation highlights for the astronomical events in March 2021. I better stand here and go see here because it's quite. Okay, so what's up in the March night sky? We will see a few events happening in chronological order. Tomorrow night, 13 March, Saturday. Hello. Hello. Yeah, we have the new moon. Sorry, previous slide. Yeah, the new moon is quite significant, especially it's helpful to astronomy because there'll be lesser light pollution in the night sky. I'll give you a good example later. Then 16 March Tuesday there will be a crescent moon near Uranus. 19 March Friday there's a Moon-Mars conjunction. I will give you the why is it important later. And of course, a very interesting thing in March is every year around the same time you have the spring equinox. It's a good time this year because you can see the Lunar X. And 24th March, there will be another feature on the moon. So largely it's about the moon for some reason. Yeah. Okay, the new moon. I believe you all know, or if you don't, that's okay. Right. The new moon is something when the moon is between the Earth and the Sun. So as shown in the top right corner, you can see that. So basically, the side of the moon facing the Earth appears to be flat. In practice, you see a very thin crescent. Very thin, but actually you can see it. Yeah. The length of the lunation is about 29.53 days. The exact number is just below there, 29.53.0588, whatever. Okay. So that's an approximate formula for you to compute the mean moments of a new moon. So you want to find D. D is the number of days passed since 1st January 2012 AM, so 0000. So given the year and the month, okay, I have an example below there. So this year is 2021. And therefore it gives you the year in the N formula is 2021.20833. So therefore you calculate the integer N and that gives you approximately 262. So through some calculation, very simple high school arithmetic here, you get that it's really very simple. You know that so that would be 7,742 days from 1st January 2000 to our upcoming new moon. So that falls on the 13th day of March. This is a very interesting but very simple formula for approximation of upcoming new moon. Yep. Okay, crescent moon. This is an example that I want to use. Why is it so interesting that you have a crescent moon and a new moon for astronomy observations? So on the 16th March, in the western sky, the crescent moon will be positioned several finger widths just to the lower left, or that's the celestial southwest, of the planet Uranus, allowing both objects to share the field of view of the binoculars, which is the red circle as you may see. But unfortunately, right, I don't think that's possible in the context of Singapore because binoculars is just not enough to see Uranus in Singapore. But although you can use telescope, normally, right, we sit by the moon makes seeing the magnitude 5 Uranus, which is actually a pale blue dot, quite difficult. But fortunately, it's a 12% illuminated crescent moon, so it won't be excessively bright. So by right, Uranus should be a pale blue dot, but according to some sources like that, it appears to be a white dot in Singapore because of light pollution. So it's like coral reef, like whitewash. It should be different color, but whitewash. That, okay. 19 March, I think this is quite an important day. So you in the southwestern sky after evening, just after evening, right, you will see the waxing crescent moon and Mars and another star, Aldebaran. Reminds me of Capybara. Will form a triangle. Yeah. So you look for the reddish medium bright dot of Mars, which I think hopefully you all can try because it's quite interesting to see a different picture of the planet. To the lower right, or 3 degrees to the celestial northwest of the waxing crescent moon. The two objects will appear together in the field of view of the binoculars, just like the Uranus example just now. So that's the red circle, you can see. Okay, 20th March, which is just, I think one day after the Mars thing. That's the spring equinox, which is quite a huge thing if you are in a farming agricultural society. But if not, then never mind, it is a good day to remember, right? Yeah. So the spring equinox is when the Earth's subsolar point crosses its equator, moving northwards. So what does it mean by subsolar point? It's basically when the sun's rays strike the Earth's surface at a perpendicular, it's like at the very point, directly above it. So I think we just go closer to this. So that's March 21st. You can see that. You can see that. That's when the sun's rays is almost over the equator. So that's the day of when, if you're in the northern hemisphere, you roughly see an equal amount of daylight. So the day and the night is quite even. Like, is that true in real life? No, that's not true. Because in real life, right, because of the atmosphere got some diffraction, so your daytime is still slightly longer than nighttime. Yeah. And then, then afterwards, the daytime will continue to lengthen and lengthen and lengthen until the summer solstice in June. So you can see that the Earth, just move in the direction until the sun's subsolar point slowly move up to the, I think that's the tropic of Cancer. Yeah, so that's for June. So that's the summer solstice. It's very important because by right, spring equinox, if you're in agricultural society, right, it's actually a time that you all should start to farm really. Yeah, so it's the middle point of spring. Yes, there are 45 days before this and 45 days after this of spring. Yes. Okay, sorry, this is very interesting to me. I think I'm a farmer by nature. Okay, so 20th March is also the same day, the night of the spring equinox. You're able to see the Lunar X. For astronomers, right, a cool place to look on the moon's surface is usually along the line between the light and the dark. You all can see, right, the light and dark, yeah, which is known as the terminator line. Yes, sorry, this is very bad joke, but terminator line, like terminates, yeah. Several times a year, right, the Lunar X becomes visible in strong binoculars when the rims of 3 craters, they are actually illuminated at a particular angle of the sunlight. So they form a small but very obvious X shape, which is about 1/3 the way up from the southern pole of the moon. I mean, if you all have experience coming to the previous sessions, you all may be asked to try to find the X on the moon. So actually, that's the X of the moon. Yeah, on the top right corner, it's a cross thing, which is actually a case of pareidolia. Pareidolia is the human tendency of the mind to discern like familiar objects. So you find smiley faces everywhere somehow. Yeah, a good example of that would be constellations. You find like animal shapes in the night sky. Because you think that it got meaning, actually it's no meaning. Yeah. Okay, after that, another feature which is the last feature I will highlight today, is also on the moon, and it's also along the terminator line. So it's Sinus Iridum's golden handle. Sinus Iridum means the base of rainbow. Somehow. Yeah. It's another visible feature on the terminator line, and you show a golden handle. So if you look to the rightmost picture, I don't think you all can see it from here, it's too far away, but you see a very small, it's like a white handle thing. Yes, it's because of the high peaks of the lunar mountain are light by sunlight, and therefore they appear as a bright arc right beside the dark plain of lava known as the Sinus Iridum, the Bay of Rainbow. So the leftmost picture, that's actually the place, but it's the arc there. It appears to be a small white arc thing along the terminator line, which I think if you all got the chance, you can look for it. So like I said, the terminator line is a very cool place for beginning astronomers to look at to the moon. You can find many interesting features that you cannot see if you are without binoculars or other equipment. Okay, so I guess that comes to the end of my observation highlight thoughts. Thank you so much for the attention. Any questions? If not, I think hopefully the sky is clear, but I don't think so. I was checking the weather and I think it sucks, right? But we all can go out and feel the wind, right? I mean, what do you think? Shall we? Cloud gazing. Cloud gazing, yes. Cloud gazing. Okay, what does this cloud look like? What animal?